Good morning, everyone. Today, our presentation will focus on the fascinating topic of the Hohmann transfer orbit and the challenges of interplanetary travel to Mars. The title of our presentation is The Physics of the Hohmann transfer orbit to Mars. So, our team consists of me, AFIQ, Arif, RUSYAIDI, and HANIF. On this slide, we can see a diagram of the Hohmann transfer orbit, which is a key concept in the planetary travel. The diagram shows the elliptical transfer orbit connecting Earth's orbit and Mars orbit around the Sun. The Sun is positioned at the one focus of the elliptical path. So the spacecraft begins its journey at Earth, traveling along the transfer orbit. The trajectory is carefully planned so that the spacecraft arrives at Mars orbit just as Mars reaches the same position in its orbit. This precise alignment is called a transfer window, and it only occurs approximately every 26 months. So arrows on the diagram illustrate the spacecraft's trajectory from Earth to Mars, showing how it follows this efficient path. The reason the Hohmann transfer orbit is widely used is that it minimizes the amount of fuel and energy required for interplanetary travel compared to other trajectories. So, by understanding this fundamental concept, scientists and engineers can design missions that are both cost-effective and practical for exploring planets like Mars. Okay, this slide highlights some key equations and values relevant to interplanetary travel, particularly for launching a spacecraft from Earth and reaching Mars. Firstly, we can see the equation for orbital velocity, which is V equal to CERT gm over r. Here, g is the gravitational constant, m is the mass of the celestial body, and r is the radius from the center of the body to the spacecraft. So this equation helps calculate the speed needed to stay in orbit around a planet. Next is the equation for escape velocity. So escape velocity, the equation is V equal to CERT 2 gm over r. So this is the minimum velocity required for a spacecraft to overcome its gravitational pull and leave its orbit. For Earth, this escape velocity is approximately 11.2 km per second. The diagram on this slide illustrates the difference between Earth's and Mars escape velocities. So we can see here is Mars has a much smaller escape velocity of about 5 km per second due to its lower mass and smaller size. So this difference plays a crucial role in planning the spacecraft's launch and landing phases. This equation and values are fundamental for determining how much energy is required to move the spacecraft from Earth's orbit to an interplanetary trajectory. Without precise calculation of escape velocity, orbital velocity, and gravitational influence, a mission to Mars would not be feasible.
Now, let's calculate the journey to Mars. The semi-major axis of the transfer orbit is 1.26 astronomical unit. Using the Kepler's third law, the total orbital period is approximately 516 days. So the one-way trip takes 258 days. During the journey, the spacecraft travels at speeds of 32.7 km per second, relative to the Sun when leaving Earth, and slows to 21.5 km per second near Mars. Retro rockets adjust the speed to match Mars's orbital velocity. The total change in velocity for the round trip is 33.4 km per second, requiring an energy expenditure of 2.84 times 10 to the power of 11 joules.
For the influence of gravity, the gravitational sphere of the Earth is 9.2 times 10 power of 8, which is smaller compared to Mars, 5.7 times 10 power of 8. When the spacecraft approaches Mars, it enters the planet's gravitational sphere of influence, which extends about 5.7 times 10 power of 8 meters from its center. This is where Martian gravity dominates the Sun. To land on Mars, retro rockets are used to reduce the velocity of the spacecraft to safely enter the Martian atmosphere. The gravity pull of Mars helps in these maneuvers minimizing fuel consumption.
After a 460-day stay on Mars, the spacecraft begins its return trip to Earth. This requires careful timing to ensure Earth and Mars are aligned, with Mars approximately 74 degrees ahead of Earth at launch. Next, the spacecraft also used another Hohmann transfer orbit return. On approaching Earth, its slow jumps using retro rockets are aerobraking through Earth's atmosphere to safely re-enter. In this interplanetary mission, which is journey to the Mars, there are many challenges scientists going to face. One of them is fuel. Over 90% of the spacecraft mass is fuel, and the energy cost is massive to launch from the Earth and then to the Mars. And this also affect astronaut health. Long duration in space also pose psychological and physiological risks for astronauts. Last but not least, in conclusion, mission to Mars depend on precise applications of physics, including Kepler's law, Newtonian gravity, and orbital mechanics. The calculations are complex, but they bring humanity closer to exploring the frontiers in space.
Thank you.